Okay, so before continuing with the lecture, I would like to say a couple of words because half of the class just arrived. We could not announce the exact room on the airs because this classroom was not listed as one of the classes, so that's why I sent an email yesterday about the classroom change, and some of you probably have not checked their mails, and those went to the other room. So just to briefly capture what I said related to course was mainly, I will repeat, there are no labs for this week, so labs will start next week. And then for attendance, you can see the details of the things on the slides, but just to give a brief overview of that. The attendance is mandatory to both classes and labs. If you miss more than one lab, you will fail the course. Again, if you miss beyond a certain threshold of classes, you will also fail. So be sure to be here throughout the summer semester and attend the classes regularly. This is going to be beneficial for you in terms of your grades and also for passing the course. So we captured in the first class, we captured what are we going to cover throughout the semester, and then what has been covered in CS 101, just a brief review of what was the topics in 101. But we will do little reviews as we go in the first 6-7 hours or so. So you will at least close the gap if you have during that time. Again, if you didn't perform well in CS 101, your success mostly depends on your efforts, because this course is going to depend on what you know about CS 101, and it will assume that you already know those topics. So if you have, if you're lacking in terms of knowledge from that course, you should try to close the gap and make up for the things that you don't know exactly. So I strongly recommend you to study while we're continuing on this course. Go over the topics on CS 101. So going back to the slides that we were covering, the program development, as we said, you are going to be required to write a quality product, a quality software at the end of this course. As a group, you will design a certain program that achieves something. For example, if you decide to write a game that teaches students, the young students, a math concept, for example, multiplication, or you want to design a web page, a web-based implementation that does, let's say, student information system, something like that. Whatever you design at the end should conform to certain standards, and these depend on how you develop the code or the program itself. So we have several program development stages. So you have to first decide what kind of language or programming environment you're going to use to write your program. Once you select that, you're going to translate the program, the idea that you have in mind, to a thing that can execute in the computer. So you have to, once you have the idea, you have to decompose it into certain parts that are implementable by the computer or the software. And if you have errors while you're implementing this, you have to revert back and solve those problems and change whatever is needed to change. So you can have software helping you all these design process, but eventually it is your job to do these tasks by using, obviously, alleviate what is provided to you in terms of software. So when you look into the programming environments, what you see is that we have, actually it's written for, but I'm not going to talk about that. We have certain levels of languages, such as the machine language, assembly language, high-level language. So what does machine language mean? What does it stand for? So it is the language that the computer actually speaks. For example, for a certain processor, you have a certain language that the processor itself speaks. So this is the machine language actually is implemented using binary values, zeros and ones, right? So whenever you give a certain instruction to a processor, let's say you would like to add two values, what is going to happen is that whenever you write the code in Java, it is going to be converted to, at the end, to a machine language, which is going to have some sort of, let's say, if the machine uses 32-bit representation, so it's going to have 32 ones and zeros. That indicates that, hey, you're going to add these two numbers. So it is going to refer to, let's say, this is assembly language. So I'm just showing you. You don't need to really, really memorize or understand it in detail. But what this is referring to is an assembly language code. It tells you that, hey, I have a value here. Let's say this is 5, R2. It's kind of a variable or a register in processor. And then I have another variable here, 3. And I would like to add these two and store the result in this variable, which is again another register, R1. So it's going to add these two values and then store the result on this register. This is the assembly version of what you are trying to do. Let's say I have x equals y plus z. And then my y is 5 and my z is 3, and the result is stored in x. So these refer to the corresponding register values in assembly. This is high-level language. This is the assembly language. And then this assembly language code is actually converted to 32-bit 1 and zeros, whatever that representation is. So the computer, the processor understands this language. So it needs to see them as ones and zeros. So how are you going to convert whatever you have, x equals y plus z, into this form? So that is the compiler's job. Compiler takes the responsibility and converts whatever you have as a high-level language and converts it into the machine language. Okay? So that is the compiler jobs, to convert this into the binary form. Okay? So everything that you write at the end will be converted to ones and zeros so that the processor will be executing, will be able to execute. Obviously, since this is a machine language, every machine has its own language. So let's say if you have an Intel processor, x86 instruction set architecture using Intel processor has its own language, whereas Sun Microsystems has its own language. So whenever you have a code that you've written here, this will be converted certain binary representation there, and then another machine language representation here. So these are going to be different from one another because they speak the different language. Okay? So you have separate compilers to compile. As you can see, this gives you a lot of flexibility and easy to program property, because once you write your machine language, you just use the compiler and generate this machine's executable, and compile it again, generate this machine's language. Right? So this is flexible. Java adds another level of flexibility, as we will see shortly. So each type of CPU has its own specific machine language, and our compilers will be able to convert these into the level of the machines. So when you look into the other levels, these are basically created for us, for the programmers, for the users, to be able to easily write programs. So by using this high-level language or assembly language, the first step was instead of going directly to the high-level language, in 60s what they have designed was an assembly language level. So they have not gone to this far around that years. So they had the assembly language first, and then they developed the high-level languages afterwards in order to make life a lot easier for the programmer or the user. So again, each type of CPU executes a single type of machine language, and then you have to translate your code into the machine's language, and to do that we use a compiler, which is a software which checks, hey, you have written x equals y plus z, then I'm going to convert this to the corresponding ones and zeros. So it analyzes the code and then converts them into the binary form to be able to be executed in the machine itself. So, for example, in Intel, let's say Intel's machine language remains to be similar so for the years, although they add additional stuff onto the instruction set architecture, it is still close to what was originally at the beginning. So they try to keep at least the language as same as possible. However, the Java approach is somewhat different. What do we do in Java is that it is, if you recall, I have the source code, I compile it and generate the machine language. Compile it, generate the machine language. However, in Java, what happens is that you put another level in between these two, machine language and then the source code. What is that level? If you remember from CS 101, we have an borderline that sits between those two levels, which is the Java virtual machine, right? The JVM. So whenever you compile your code, you actually compile it to the byte code, if you remember. So when I have a code that, let's say I have test.java, when I compile it Java CC and compile that, I will get test.class, which is the Java bytecode. So this is converted to the machine code of the Java virtual machine. So JVM is going to be able to execute this code, the generated class file. How am I going to run this on the software or on the hardware that I have in terms of the CPUs? This JVM is installed on both this environment and then this environment. And whenever you have your test class, it's going to run here and there as well, so that this JVM converts it to the corresponding architecture. Okay? So this is the basic technology that's underlying in Java, right? Any question? So Java bytecodes is generated. They run on JVM. JVM actually converts them to the machine language. So whenever you try to run a Java code, you see that if let's say in a Windows environment, if you do not have the JVM installed, it is going to say you that, hey, Java is not installed, you have to install Java. So that's why you need to install the Java, because you don't have the corresponding converter from the Java bytecodes into the actual machine code, machine language. So JVM will be installed in different processing environments. The advantage of this is that, what's the advantage of this? Once you have the application test.class, this can run on any processor that has JVM, obviously. If it is an Intel processor, it will be able to run on this computer because it has the JVM, so it can run. This will also be able to run it if it has the JVM. So once you have this application created, you can send it and run it anywhere you like. So that gives you platform independent execution. So you don't depend on the platform. It runs on every platform you have. Okay? So this JVM actually interprets whatever you have is in bytecodes into the machine language. So that's why we use the JVM for. So I will have here a small figure that represents what is done here. So you have the Java source code, and then the Java compiler again generates the Java bytecode. So you generate the Java bytecode. This is then used by the JVMs, the bytecode interpreter, into the machine code. So this is a separate machine, this is a separate machine. Whatever this machine uses will be converted by the interpreter that you have into the corresponding machine code. Okay? So whenever you write your code, there are various environments that you can use to implement your software on. So these are just examples: IBM Eclipse, Sun, JDK, Borland, JBuilder, JCreator, as we use in the classrooms, or other software available for you to execute and run your code in Java. Obviously, they provide, depending on the tool you have, debugging options, flexibility in running the applications and things like those. So they have their own flexible implementations which are useful in many ways, because, for example, if you need to debug a certain code, this software might be really helpful. For example, if you're able to watch some of the identifiers. Let's say you have a program that runs and then you are not certain about the value x, let's say an integer value, what it has throughout the execution of the program. You can watch this by the software and see what is the next value of this identifier or the variable, and then see accordingly if your program actually works fine, right? So they provide good debugging options for you to use. But at the end, it depends on you to, write a good quality code and implement it in an elegant fashion. So syntax and semantics. What does syntax stand for? What does syntax mean?
Grammar rules of Java language.
Exactly. So it is the grammar language, meaning that as we use in any natural languages as well, you have certain rules. This has to come before this, and there must be a punctuation here and there. Those type of things are called syntax of the code or syntax of the program. So you have to have the syntax correctly. If you do have a syntactic problem, whenever you try to compile your code, you're going to get a error saying that, hey, there's a problem on this line. Let's say, for example, if I would like to write a for loop. Let's say I have a for loop that I'm going to write for int I equals 0, and then that is all I would like to write here. And I have the inside of the for loop here, and what is going to happen is that I'm going to get a syntax error here, right? There will be a syntax error. Why?
There is one more semicolon.
I need to add another semicolon on this for loop because there are 3 components, if you recall. One was this, and then if you have a condition, you will put that there, and then you will, if you have afterward statement that you would like to execute after every iteration, you will have that here. If you don't have those, what you need to have is just empty spaces and add the semicolons. So you have to have these 2 semicolons even if you don't have anything in between. So this is going to, if you do not have this semicolon, you're going to get a syntax error. So this is syntactic problem, and your compiler will raise an error here saying that, hey, there's a problem. You have to then semicolon, and that will solve the problem. Usually syntactic errors are easy to resolve, easy to find, and easy to modify. So they're not usually a problem in implementation. However, the more important part is the semantic. So whenever you write something like this, is it doing what you're trying to do? That is the issue. So that is the semantic, the meaning, the internal meaning of what you're trying to achieve by writing this code. So both syntax should be correct and then semantics should be correct, meaning that after this for loop is executed, whatever you wanted to achieve, is it achieved or not? That is the idea of the semantics. Usually, this is where you make more errors and see more problems, because you think that you're performing something here. However, in actual real life, you're not really doing that. You have some kind of a problem. So the program will always do what we tell it to do, not what we meant to tell it to do. So it doesn't matter what you mean, but what matters is that what actually you implemented and what you wrote there. So that's semantic issues are important. So there are 3 types of errors that you can have in a program. One is obviously the syntax errors. Again, these are easy to find. The compiler will easily locate those errors and you will easily fix them. However, you may also have runtime errors. Can you give an example of a runtime error?
For example, denominator is, when denominator When denominator is 0, this is runtime.
Exactly. So if you have a divide by 0 operation that you're performing in your code, then you're going to have a runtime error. Normally, let's say you ask the user, let's say your program is asking the user to enter the first number. First number. User enters 5 and then enter the second number. User enters user enters again 5, let's say. The result is, it prints, result is 1, divides 5 by 5. However, what if you have a 0 here? It is going to cause an exception. It is going to cause an error saying that, hey, this is a divide by 0, and then you will receive it, instead of result is statement, you will see that there's going to be an error raised at runtime. So this is a problem. So to resolve this, to correct this, for example, if this is written as return x divided by y, what you could do is you can add an if statement on top of this, right? Saying that if y is not 0, then return x over y, right? So you can prevent this by adding such a clause at the beginning. So this is a runtime error, and usually it is sometimes harder to identify what caused this runtime error. Although it is not that hard, but sometimes still you see that you may not locate the exact problem. And the logical errors are the worst ones, because you think that you're doing everything correctly and the program runs just fine. However, you may find your algorithm or the program to incorrectly execute the result. For example, let's say you wrote a sort algorithm and you would like to sort an array, elements of array, and at the end return you the sorted array. Let's say if your code actually runs in such a way that it returns you 3, 6, 5, 7, then there must be a problem, because this is not sorted actually. So there's a logical error in your code that generates this array list. Sometimes you may not be even aware of this problem, and that is usually the case if you are having really complex algorithms and programs. So you may not even locate exactly where this happens, why it happens. So you have to go and do a true check of the code that you have. So that is why actually you would like to write your code in smaller pieces rather than having a big complex structure. So what you would like to do is you would like to divide your application, program, or implementation, whatever you have, into smaller pieces and chunks, and make sure that every piece works correctly. So this performs this task and then generates me as an output this, and the next step is performed by this. So if you know that this performs, by looking at its input and output, performs the result in a correct fashion, then you know that there's no problem on this one. And you can locate the problem easily by this way. Okay? So you decompose the tasks into smaller pieces as much as possible. And that exactly fits into the object-oriented methodology. So since we have errors, even if it's a simple, very basic program, you will at least have lexical errors, syntactic errors, which you would like to, resolve and solve the problem. So usually the case is that you write the program, compile it, you see errors, syntax errors, rewrite it, solve the problem, again compile and execute, and you still find errors. It could be runtime errors, logical errors, and so on. But at the end, you do iterate over and over to actually make your program a perfect one, and error-free, bug-free, easy to use, executable at the end. So this iteration needs to continue in order to get a good design. So the problem solving, the purpose of writing a program in the end is to solve a problem. For example, they have come up with this big database that you are using, for example, for the university, right? All of us are using the university system to do the registrations, for us to check the classes. and for example, they have all these conflicts that they're trying to resolve using the program. So it tackles a certain real life problem, and it tries to solve a real life problem. So in order to solve this problem, the steps are: you need to first understand the problem in real detail and understand what actually you're tackling to and trying to solve to, and design a solution based on that. So if you don't know the problem well, you won't be able to design a good solution. So once you understand, the next thing is design a solution. Consider all alternatives. So for example, let's say it involves some sorting in it. Are you going to use this sorting or that sorting? Are you going to use arrays or different implementations? Are you going to read and write from files or get the input from the user? So you will, consider all the options you have and choose the one that perfectly meets your criteria. And implement the solution. And at the end, this is really important, you have to test your solution. So for example, let's say we wrote the registration system here, and then somehow it registers more than the allocated student count, and the system continues to register every student who tries to get the course. Then this is going to create a big problem and a disaster. So you have to, in order to prevent this, you have to test your solution and make sure that there are no problems there. Even worse, if you think a missile program, missile execution program, which points to the exact target of a missile that is going to hit a certain area, then if your calculation is not correct, that's going to be even a bigger disaster. So you don't want to face with that, and there are rigorous tests for every program and solution, and you have to do this for any kind of application you have, depending on the importance of your application, obviously. So if you look into Microsoft's hiring, new hires, you will see that 1/3 of the engineers they hire are test engineers. So not, if you have 1/3 is design engineer, 1/3 is also the test engineers, which actually test the software that develops. So this is really important. Even with that, they still have errors. As you remember, when implementing the software, you see many problems. So these are not purely linear. I mean, they do not follow one after the other one, but usually you may need to, once you test the solution, you see that, hey, there's a problem in your design, so you go back to design and modify it and redo these tasks and test again. Or you see that implementation created a problem, you do it again. So this is not a linear but iterative process that you go over and over with the implementation of the program. So the key is designing. The key in designing is that you want to divide your program into smaller pieces that are manageable. And this is exactly what we can do with object-oriented methodology. So we have objects that we do things on, and they can interact with one another using the interactions or methods between them. And so we will try to divide, for each design task, we will try to divide the things into smaller objects and try to utilize them in smaller pieces and collect this as a whole hierarchy at the end. And in your project also, you're supposed to do it that way so that you have a good design at the end of the day. So we have in Java, if you recall, it's an object-oriented programming language. So we have objects, and we would like to use them effectively to represent the real-world entities. And for example, an employee, you have, for each employee, you have a certain characteristic for the name, ID, whatever you have as an information. And then also you have methods that you deal with the employees. So these are the two different things. When you look into these two things, we have the state, which indicates the description of the object, such as employee's name, ID, and so on and so forth. And then the behaviors, such as, for example, pay employee, a method that you increase the employee's account balance, for example. Or let's say give leave, for example. If the employee is going to take a leave for a month, then you have a leave option which you use as a behavior to give a leave to the employee. Again, bank accounts. You have the bank account name, ID of the holder, and also withdraw and deposit are the two, things that you can, two behaviors that you can play around with the account. So we have objects that we define by using a class. If you remember, class is a kind of a definition, whereas object is an instance of that definition. So you can have multiple instances of the same class, which we have seen before. For example, a class, the concept bank account, may be defined, and then you have an object that is used to implement this class. So for example, we have multiple objects such as Bill's bank account or Mary's bank account with certain specific characters. So you have the general class definition and individual objects that use this class. And in inheritance, as we will see a lot more details how to implement this, we inherit certain characteristics of the class to use in another class. So for example, you have an account class that is used in bank account and also charge account. And then you have a savings account and checking account that uses the bank account information. So for example, savings account will have all the details of a bank account. On top of that, it will have certain other properties. For example, it may have, since this is a savings account, interest rate, which does not exist in the bank account, for example. So you can, you can think of this hierarchy as you enlarge it. So this is called inheritance. This bank account inherits properties of account. This savings account inherits the properties of bank account, which inherits the properties of account. So let's say if there's a method that is defined for account class, a withdraw method, for example, this savings account can use that withdraw method if it needs to. Okay? Any question? So as I said earlier, in the end of every chapter, towards the last pages of every chapter, we are going to have graphical user interface GUI parts that deal with GUI stuff, and we will touch base those as we go. And as you know, for each picture or a drawing object you have, it must be digitally stored and expressed. To do that, what we do is, in graphics, as you know, you use pixel, right? What does a pixel do? What does pixel mean? It is the smallest information on the screen or on an image to show and to represent. So let's say if I have a screen, LCD screen, which is, let's say, 1024 by 768 pixels, so I have this many number of, so at the end I have 1024 times 768 pixels in total on the screen. And if I would like to, show a picture on this screen, what I will do is I will, map my image onto each pixel of this and show it on the screen. So every picture or every graphic interface needs to implement in this fashion. For example, if you consider a black and white picture, what do you need to store for each pixel? If I only have either black or white, it is sufficient to use only one bit for each pixel, right? If it is 1, it is going to be black, let's say. If it is 0, it will be white. If it's a black and white screen or black and white image, 1 bit will be sufficient. However, if I have a colored image, what I would do is I will use a different format to represent that, which is usually RGB or other units or types are also available. However, RGB is the most famous and most widely used one. So RGB, what does RGB stand for? Red, green, and then blue. So what you usually see is that for each one of these colors, you have a number that it represents. And from a scale from 0 to 255, it represents the density of or intensity of the color. So red will have from 0 to 255. Okay? And then you have a value for green, 0 to 255. And then for blue, you have 0 to 255. If, let's say, I have a color RGB value, which is 255, this is going to be true blue. So since R and G are all zeros, you will have 255, which exactly represents the blue. And all these colors and its different forms are represented this way. So when you look into this case, for red, how many bits do I need to express in order to express this red color? Since there are 256 different options, you have to have 256 equals 2 to the 8. So I need to have 8 bits to represent my red, 8 bits to represent the green, and 8 bits to represent the blue. So I will have in total of 24 bits to represent each pixel value. Okay? So if you consider, for example, one frame with this many pixels, what you need to have is 24, this many number of bits is needed to express only one frame. Consider a video, for example. Consider a video. How many frames usually a video has per second? 24 is kind of a universal, number. So you have 24 frames per second. As you know, if you go beyond this value, the eye is not able to capture this anymore. So this is already sufficient value. If you go below this value, let's say 12, 10, you see that the image is coming really, one after the other one, and you can identify this change. So if you consider this, you see that for every second, this is frames per second. So if you multiply this with the 24, you see that this many data needs to pass through your screen in order to, your graphics card, in order to be able to see this video. So as you can see, a lot of data is going on, and that's why the graphics processors are really getting intensive and, getting more expensive also in order to implement these. Because we're looking for increasing the number of the pixels that we have on our high definition, and increase the number of also colors. So this adds more and more data as you go. So we have to use pixels and digitize the images or videos or whatever we are expressing as graphics on the monitor in terms of in order to show them in a nice fashion. So in the two-dimensional screen, what we express each pixel is using by x and y coordinates. These are the two dimensions we have, and the left topmost corner is the 0 point, or the origin that we have. And then for each point, you identify that location by giving the coordinates, as in this case 112 and 40 to express this point is shown. So whenever you, let's say you would like to draw a line starting this point and another point, you need to use these corresponding points. And in GUI components, we will go into details of that in the next lectures or so. So again, this is just capturing what I just said. For red and for black and white, you will have 0 for white and 1 for black, and you can represent it with 1 bit. However, with RGB, you will have 24 bits to represent this many colors and this many variations in the color. So when you look into the color class in Java, it is represented using these RGB values. So when you look into the color.black, it is all zeros. And then color.blue, as I said earlier, 0, 0, 255. And then color cyan, it is going to be 0, 255, 255. It is a composition of green and blue. And then you have orange, which is 255, 200, 0. These are already defined colors, which you can just pick from the Java's color class and use immediately by referring to the color.yellow, here in this case, red and green forming the yellow, and so on. Okay, you can manually assign these numbers and create the color you like, but if you would like to use the predefined colors already, you can use these from the GUI library, which is part of the color class. Okay, now we will go into applets, which is also a graphical, component of the Java. Have you ever played with applets before? Nobody? Okay. So this is, these were more famous in the past than they are now. But however, still you can use them. Java application that is a standalone program that you can run on your browser, for example, in Internet Explorer or Netscape or whatever you're using as a browser. You can access these applets using that. So if a certain web page provides this applet, you can see it on the screen, and you can see the output of that. So it is intended to transport over the web and execute using a web browser, as I said earlier. And you can execute this applet using applet viewer tool, or again in any browser that you have installed on your computer. And it doesn't have a main method. This is different from what we have done so far. Instead, there are several special methods that service specific purposes. What are these specific purposes? For example, the paint method. It is automatically executed when you draw the applet and its contents. It is automatically executed as a result of this applet execution. I will show an example in the probably next lecture. How many minutes do we have? Okay. The paint method accepts a parameter that is an object of the graphics class. So let me continue with this a little bit more. So you have a graphics object that defines a context on which we can draw shapes and text. So you can add shapes such as a line, a rectangle, or a text that you would like to put on the screen. And also you can have shapes that you draw, as I said earlier. So you can have a class that extends the applet class so that you have inherited the properties of the applet class. And we will see this in more detail in the chapter 8. And for example, we have Einstein.java that is an applet embedded into an HTML file using a tag that references the bytecode of the applet. So let me show you that example, and then you have an idea what I mean by this. Okay. So let's go, and so this is what it looks like. Okay, so this is the Einstein applet, and then this is actually where applet is plugged in. So this is a Java code that is embedded in the web browser, Einstein.html, and then this is the regular web browser's code that is embedded in the HTML code. If you go ahead and see the code of this HTML file, so if I go and open with, let's see, what do they have sent to? Okay, so let's go here. If you look into this one, so you have the HTML tag, title, Einstein applet title, and then the head is finished. Okay, and then the body starts. So you have this header, H3 indicates that this is going to have a certain format in terms of the header. And then you have the applet code. As you can see, applet code is embedded using this. So you have Einstein.class, and then you have the width and height of this class that you would like to embed in there. And then this applet is finished here. Then the actual text you just seen, starts afterwards. So that is representing what you have here. Obviously, you have to refresh in order to correct it. So you have the title on the center, and then you have the applet, and then the text followed by that thing. So when you look into the code of this applet, let's open this up. So when you look into this, it uses the Java GUI libraries such as the Java Swing JApplet, and then the AWT, Advanced Windowing Toolkit is the the open form of it. And it has public class Einstein extends JApplets, so it uses the applets library. And if you look into the paint method, I will go over this again. So you have, as you can see, the paint method. Within the paint method, what you have is draw rectangle, 50, 50, 40, 40. I will explain each of these in more detail. And then you have draw rectangle, another one, draw oval, draw line, and draw string out of clutter, find simplicity. So you add the text, and then another text, Albert Einstein. If you go back and see the HTML version of it again, as you can see, this is the rectangle, this is the other rectangle, this is the line, this is the circle, and then you have the text written on these two lines. Okay, so we will see in more details how you achieve this applet execution in the next lecture. So that's all for today. See you next time.